Hi, vanakkam. Let's talk about why Pythagorean theorem uh, is only been proved, or why it specifically says that the triangle should be the right angle triangle. So let's see it visually. For our reference, I have the right angle triangle with us, as you can see. This particular triangle, if I select it, if I put it exactly, snap it on the grid, as you can see, it has three sides, out of which two sides are perpendicular to each other. Let's name them. So let's say this is base, so side B, and this is A, and that makes this hypotenuse, which is C. So this is a triangle with sides A, B, and C, in which sides A and B make right angle to each other, or they are perpendicular to each other. Now let's visually see why a square plus b square, which is our Pythagorean theorem, which says a square plus b square is equal to c square, stands true for the right angle triangle. In order to do that, we'll have to create a square whose side lengths are a and b, because geometrically speaking, a square signifies the area of the square whose side length is a. Okay, so I can just grab my polygon, and maybe I can snap it around here, and I can, since the length is 4 units, I can make sure that I can create a square using 4 units line on each side. And for b square, I can grab another polygon just real quick, and I can create a square with side length of 3 this time, because the length of side B is 3 units, and I can color code it with the same angle. Now here, if I have to measure the side length of the hypotenuse, I can quickly grab my ruler here, and I can see that this is 5 units. What I can do is, since the hypotenuse is not exactly aligned to the grid, I can just draw a perpendicular line on both sides. And just select a line and draw a perpendicular line, and make sure I am at 5 units here, and I can try to create a polygon. Okay, just grab it real quick, and I can snap it simply to the vertex or vertices. There you go, exactly, and make sure exactly 5 units. And just to be sure, I can just check the length. Yep, it's 5 units. So now I have the third triangle, which is whose length or side length is C and the area is C square. I don't need the perpendicular lines anymore, so I can just erase them real quick. And I don't need the ruler anymore, so I can delete that. Now, to see how a square plus b square can be c square, I can simply grab my a square and try to fit into the b square. It's a bit tedious task. Or I can also maybe cut or slice, maybe through diagonally, and maybe try to fit that in over here. And okay, that's one way of looking at it. It's a bit of a iteration, you can see, but I'll just grab all this real quick bit away from it so that we can try and fix it here. So I just try to cut it and fix it here. I just try to cut my triangle and try to fix it here, and all I need to do is try to see if I can fit my b square. And as you can see, I can fit it right here. Yeah, and maybe I can use the cut tool here to make a small cut here, and I can maybe cut over here as well on this line, and I can keep on going like this and try to fit this, you know, in a way that is visually more appealing. So you get the idea that if I have to fit everything in the C square, as you can see I have the outline now, if I keep at it after some point of time, I'll be able to fit in this whole B square inside my A square. So maybe I can do a real quick cut one last time. This is a bit tedious, I know, but flip it like this. Maybe I can try and fit this particular angle here, and I'm left with small pieces which I can use again to using my cut tool. Oops. So as you can see, this is not exactly precise, but I'm getting there. With few more iterations, I'll be able to fit my B square inside my A square. So I'm going to stop right here. Looks like a kite. So yeah, but let's try this in case of obtuse angle. I took a liberty of creating the triangle, creating the squares adjacent to each side. As you can see here, this is obtuse angle triangle, in which one of the angle is more than 90 degrees. And as you can see visually, that if I try to grab this square and if I try to fit it into another square, as you can see, I have ample space for another square. Even if I grab my cut tool to slice some of the area, as you can see, maybe I could turn it around. As you can see that I could perfectly very easily be able to fit two squares, A square and B square, inside C square. Plus there is a lot of empty space. So I can clearly say that in this case, when I add the areas A square and B square together, they're clearly smaller than C square. So my C square is clearly much bigger than the sum of the areas A square and B square. That's why Pythagorean theorem doesn't stand true for the obtuse angle triangle. Let's quickly see one more example with acute angled triangle. Acute angle triangle is the triangle in which all the angles are less than 90 degrees. So as you can see here, visually, all these three angles are less than 90 degrees, and hence the three squares. So if I can quickly name, since I've already color coded, this is my side B, this is A, and this is C. As you can visually see itself in this case, is I can clearly say that A square is definitely bigger than C square itself. So there is no question of fitting. I can simply fit B square. They look quite similar, and as you can see, my C square is almost full and I don't have enough space for A square to fit in C square anymore. So I can say in this case that my A square plus B square is definitely far greater or bigger than C square. So in case of acute angle triangle, the technically hypotenuse, or one of the sides area for that, is definitely smaller than the sum of the square of the areas of other two sides. So hence the proof that Pythagorean theorem only stands, or whenever we talk about Pythagorean theorem, we specifically make sure that we are talking only about the right angle triangle, because only in in the case of right angle triangle, I'll do a better job probably next time fitting these angles together. But in this case, we can say that the areas of both the sides when we add them together is equal to the area or the square of the third side. I repeat, the squares of the sum of the squares of both two sides which make the right angle triangle is equal to the square of hypotenuse in case. So that's the Pythagorean theorem, and it proves true for the right angle triangle and not for the obtuse or acute angle triangle. I hope this makes your understanding clear visually, and I hope to see you in the next video where we talk a bit more about practical applications of Pythagorean theorem. Till then, happy exploring.